Hello and welcome to another video. In this problem we're going to be working on design graph with shortest path calculator. And in here you have a directed weighted graph that consists of n nodes labeled 0 to n minus 1, and you have some edges where each edge is from, to, and the cost, meaning there's an edge from to to with some edge cost. And you want to implement the graph. You want to be able to initialize the graph, you want to be able to add an edge, and it's guaranteed that you won't have a duplicate edge. And you want to find the shortest path between two nodes, which will return the minimum cost from node 1 to node 2. If no path exists, return -1. Cost of a path is the sum of the cost of the edges in the path. So this problem is basically, I'm not really going to go into the example because I don't think it's necessary. This problem is basically a cookie cutter Dijkstra's algorithm. I actually did need to look up how to pronounce it because I wasn't sure if it was Dijkstra's or Dijkstra's or whatever. And I honestly wasn't sure for like the last, a long time. So I wanted to look into that. So it does turn out to be Dijkstra's. So anyway, this add edge is very, very simple, right? Like we just add an edge. So if you just have something to represent a graph, it's very simple. And the real crux of this problem is this shortest path. And that's pretty much what Dijkstra's does for you, right? It pretty much solves this problem of given a start and an end, find the shortest path. And if it doesn't exist, you'll also be able to do that. So it's going to be pretty simple. The way we're going to store our nodes is we're just going to have a from, that's going to be the key. And then in our values, we will just have an array of arrays, and it will be to, right? So it'll be like from to, and then this will be the cost. And we'll just have a bunch of these, right? So for example, for 0, we are going to store like 2, and then cost 5, we're also going to store 1 and cost 2, and so on. And this is how we're going to represent our graph. So we're going to take our edges, make this adjacency list. Pretty straightforward. You would do this for every single graph. And then from there, we are going to do Dijkstra's algorithm. And essentially what you do is you have a starting edge. Let's say we start at 0. Actually, let's say we start at, because this one's kind of small, let's say we start over here, and we're trying to get over here. So basically what we end up doing is we make a heap with a node and a path length. And the idea of the algorithm is you keep track of all of the nodes you're currently at and the path to get there. And you just keep taking the one that has the smallest path. You're essentially saying, okay, give me the smallest path and I'll try to go there and I'll try to visit nodes next to that. So we're also going to have a visited set. So we'll call this maybe like V. And essentially, let's kind of walk through what this would look like. So we started out with node 3. So we're going to have this heap. And it's going to have the path length first because we want to sort by the smallest path. So we'll have a path length of 0 at first because we're just starting at 3. And then we'll say this is node 3. And I'm not even going to have this. I think what I'm going to do is I'm not going to have this like closed bracket just so I can fit everything. But essentially, all of these are going to be in a heap. So we will actually don't need this. So let me get rid of that. And yeah, okay. So what we're going to do is we're going to pop the node, right? So we're going to pop this node, and we're going to check, is this our end goal? And our end goal is this in this case. And so here it is not our end goal node, right? So we're going to add it to the visited set. So we'll add 3. And then we are going to look at all of the nodes that we can go to for 3 and add them to our heap. And when we add them to the heap, we're going to add the distance from 3 to those nodes plus the distance it took to get to 3, which will be like in this heap. So it didn't take anything to get to 3, so we started at 3, so we're going to pop this 3, and we're going to say, okay, what are all of the nodes that you can get to from 3? Well, you can get to 0, so we're going to add 0 and the distance, which is 3. So remember, it's going to be distance node, so we're going to add 3, 0. So we got rid of that. That's basically all we can get to from 3. Okay, and so now for 0, and this is already in our visited set, so 0 we're going to pop. We're going to say, is 0 our end goal? No, it's not. So let's add 3 to our visited set. Oh, and by the way, when we pop, if it's in our visited set already, that means we've already like been here. And if we've already been here, then that means the path that it took to get here is shorter. So if it's in our visited set already, when we pop, we can just continue. So we'll add 0, and we'll say, okay, what are all the neighbors of 0? So there is 1 and 2. So we will first, let's say, add 1. So we will add 1 with, we'll add 1 with, and this path length is 2, but you need to add the path length it took to get here, right? So the path length it took to get here was 3, so we'll have 3 plus 2, so we'll have 5 and 1. And we will also add the other neighbor, which is 2. And how long does that take? So the path length it took to get here, which was 3 plus 5, so it's 8. So remember, distance and then the node. So we need to add these two nodes, and we need to get rid of this 3, 0. Okay. And let's move this up here now. So this is our heap. So we're going to pop this node now, and we're going to say, okay, is 1 in visited? No, it's not. So let's add it to visited. Is 1 the node we're looking for? No, it's not. Okay. And what are the nodes we can get to from 1? Well, we can get to 2. So, and notice just because it's in our heap doesn't mean we shouldn't add it in, because we might have the node already, but the path to get here might be really long. So actually, you still want to add the node even if it's in the heap. You just don't want to add the node if it's already been visited, because if you actually visited, that means we've already been at the actual node. But if it's in the heap, you definitely can want to add it in, because let's say 3 has a path length to 2, that's like 1,000,000, right? 2 would be in our heap, but that's not going to be the shortest path. So yeah, so we're going to pop the 1, we're going to look at the children, we're going to say, okay, we have 2, path length of 1. That means what we need to do is we need to add whatever the path it took to get to 1, which is 5. So 5 plus 1, 6, and 2. And now we get rid of this 1, and that was the only child. Or there's actually child 3 here, but we already visited 3, so we don't need, that's the one we wouldn't need to add. So 1 does have this child 3, but we don't need it because we already visited that. So we're guaranteed to get a worse path than we already had. Okay, so now we're going to take this 2, and we are going to put it in a heap. So then we're going to get the smallest path here, shortest path again, and we're going to pop this, and we're going to say, okay, is this the node we're looking for? And it actually is a node we're looking for, so then we can just return the distance. And so the distance is 6 here, and that is correct because it's 3, 2, 1. And that's essentially how you do Dexter's algorithm, is you just put a starting node with a path 0, and you just, every node you pop, you make sure, like, have I been here before? If yes, we can even write this down. So have heap initially with 0 for path, so path equals 0, and node, starting node, source, and every iteration pop node, if visited, skip, if not, go through children and add all children that haven't been visited to heap with path equals path from node to child plus path to get to node, right? That we have stored original in our heap. And then that's pretty much it. And then if we run out of heap, right? We don't have, like, we keep going until the heap is empty and didn't find destination, then return -1. So it's pretty straightforward as long as you know how to, like, build an adjacency list for the graph and use a heap. It's a pretty straightforward algorithm, and there is like another algorithm to use. It's like the Floyd-Warshall or something. I haven't really looked into that, and I don't think it's, especially for like coding interviews, unless you're trying to do like, I don't know, like code forces or something, there's kind of no point in going into the rabbit hole of like 500,000 algorithms to solve a problem. Like, I would just learn the most common ones to solve a problem and get good at those, because especially for graph, you can go really in the weeds of, like, you might learn one algorithm for like one problem that you're going to use and then throw it away, and these do take time to learn, so I'll just focus on the core ones. So that's why I decided to do this way. All right, so we can actually code it up now. So let's do that. So we're going to first have the init. So we'll just say, like, we can also, so they do give you an n. You don't really need to use it, but we will try to have like a shortcut where if our node is out of bounds, then we will return false immediately. I don't know if they are ever called with nodes out of bounds, so I don't know how much it'll help, but we'll see. So we'll just say like self.nodes equals n. So for example, if n is 5 and we get 2 nodes here that are like 7 and something, we know, like, hey, 7 can't be in here, so we can return -1. I don't know if it's actually called with nodes that are out of bounds, so maybe it doesn't help at all. But okay. So the way to populate a graph or adjacency list is going to be like this, very convenient. So you want to make a default dict, with a list, and then essentially you go through all your edges. So every edge is going to have a start. So we can destructure here start, end, and then distance. In edges, we will say self graph at the start node will append. And so, like I said, we're going to append an array of end and distance. You could do it the other way around. Our heap will actually have it the other way around, where we're going to hold distance and end, because we want to sort our heap by the first element. So we want to sort by smallest distance, but we can add this way. So add edge, very simple. So we'll just say the same kind of thing. We'll just say like start and dist equals edge, and self dot graph start dot append. So, like, honestly, I don't even know why this is a thing. It's very simple. Okay. And now that we did that, we are going to go through the shortest path now. So for the shortest path, we are going to first check. Like I said, I don't even know if this works, or like they even have things that are out of bounds, but you know, why not? So if min node 1 and node 2 is less than 0, essentially basically our node's invalid, or the max of node 1 and node 2 is greater than or equal to self.nodes, our node's out of bounds, we'll just return -1 right away. Okay. So now we're going to create our heap, and our heap will be initialized with the starting node, so node 1, and a path length of 0. And we're going to have a visited set. And we're going to say, and by the way, for this visited set, this kind of depends on the problem. So in this problem, in the picture that I showed you, there were loops. Like if you actually look back in here, there are loops. Like, let me delete some of this so you can see it a little bit better. So here, like from 3, you can go to 0 to 1 to 4. So there are loops. So this kind of depends on the problem. Like some will say there are no loops, but here there are loops. If there are loops, you need a visited set. If there are no loops at all, if you can never get back to a node you've been, then you don't need that. Okay. And so we're going to essentially say, while we have a heap, let's just keep doing stuff. So we're going to pop. And remember, a heap is going to be in the form of path and start, which is like the node, equals heap pop heap. Then if start, which is the node, was then visited, let's just continue. We've been here before. This is a worse solution than what we had. Otherwise, let's add it in. And let's also check if start equals node 2. That means we have our solution, so let's just return the path length. Now, otherwise, we have to go through all the children and add them to the heap, but we're only adding children that haven't been visited. So we'll say for end, and remember our children are in this format end, and then like node, and then distance. So for end, distance in self.graph start if end not in visited. If we've already visited it, we don't want to add it, but if it's in the heap, we still want to add it. So that's the difference between that and a breadth first search. Like if all these graphs, let's say this graph had edges that were only length 1, then you can just say once it's in your queue, you never need to add it in, because if it's in the queue, that's going to be the best path. But because this graph is weighted, just because it's in there doesn't mean it's the best path. So that's like a slight optimization you can make for a queue. If you're just doing some kind of like matrix traversal or something, you can add to visited right when you add to the queue, instead of here where you can only add to visited right when you actually visit, right when you actually pop. Okay, so if end not in visited, we will heap push to the heap, and we are going to push the old, let's see here. So we're going to take the distance from the node to the child plus the old path it took to get to the node, right? So we're just cumulatively increasing this path length and the end node. And basically, if we didn't find anything while the heap is here, that means we didn't find a path, so we'll just return -1. All right, let's take a look. Right, so this should be equals. All right. Looks like we have a solution. Pretty good. Okay. So let's go through the time and space. And honestly, I really hate doing time and space for Dexter's algorithm, because like, especially when I read editorials and look at people's solutions, people kind of disagree on the solution. So I haven't seen like the official, time and space for this algorithm. People write all kinds of different stuff. So I'll just provide what I think is reasonable. So let's go through all of these functions. So for this init, we'll have time for init. essentially we are going through all of the edges and adding nodes for every edge. So that's going to be something like O of E, pretty much, where E are at. So I'll use E for edges and V for vertices. So it's going to be something like O of E, because for every edge, you add it into the graph. And like if there's 20 nodes in one edge, you're only doing this once, so that's why it doesn't rely on the vertices. Okay, so for add edge, that's obviously O of 1. So we'll just skip add edge because that's just kind of meaningless. Like it takes nothing, it does nothing. Okay, so now we'll do the shortest path. And that will be, this is the one that's controversial. So essentially, you have a visited set and you have a heap. And worst case scenario, you will be adding every single edge and removing every single edge. And in a really dense graph, let's say every node has like n-1 edges. Basically every node is connected to like every other node or something. That's going to be E log E, because you're storing edges in your heap. So a heap pusher, heap pop costs you log E, and then you will do that E times, because essentially you might have to put on like every single edge. And realistically, it's going to be like a lot faster than this, but this is like worst case. Like I don't think it ever gets this bad. So something like this is going to be the time complexity for shortest path around here. And as far as like adding things to the visited set and so on, it doesn't matter. And I don't think it relies almost at all on nodes, because essentially to get to a node, you have to go through an edge from a node to a node. So like I think it relies purely on edges. Okay. And for the space, so this init is going to be O of E once again, because essentially you'll have some nodes, but it mostly relies on edges. So if a node doesn't have edges, it won't be in the dictionary. So I'll just say O of E again. You could say maybe O of V plus E, but basically, since it relies on edges, realistically, like I said, if you have one edge and 20 nodes, this will only have one item. So that's what I was saying. So you can say it's like V plus E if you want to, but realistically, V is going to be less than or equal to E, so I think E will be the dominant variable here. Okay, and for the add edge, once again, it's like O of 1, so who cares? Shortest path, it's going to be, so for the heap, like I said, it can hold every single edge. Realistically, it's not going to be that bad, but we'll say it's roughly that. Yeah, you could argue like edges is node squared or something, so then maybe, actually no, that wouldn't even matter. So yeah, I'd say it's like O of E for the heap to hold everything. Visited set is going to be O of N or V, but like I said, in order to get to a node, you have to have an edge. So basically, edges has to be greater than, or like, it basically has to be either equal to V or bigger. Or like V will be like E plus 1 or something, right? So either way, they'll basically be the same. You're never going to have a case where like V is like 1,000 and E is 500. E will also always be way bigger or basically the same. So that's why I'm not going to include vertices in this one. Because like I said, you can't get to a node unless there's an edge. So you can never have like 20 nodes that you visited with like 5 edges, right? And yeah, I think that's basically going to be that. So, like I said, not a huge fan of doing time and space for this one. So if you guys disagree, feel free to write in the comments. But yeah, I think that's going to be all for this one. So if you did like it, good one to practice. I think this is like one of the better problems to practice. Just cookie cutter. Can I write Dexter's algorithm? Nothing tricky. This is literally just, this problem can just be renamed to like implement Dexter's algorithm. Straightforward. Good one to practice. And then there will be harder problems where you're doing that in like some other way, or they won't tell you directly like obviously this is what you got to do. So yeah, that's going to be all for this one. Hopefully you liked it, and if you did, please like the video and subscribe to the channel, and I will see you in the next one. So thanks for watching.